Hi everybody, we're going to go over example 5 of the 8.1 notes, which is sequences. In this question, we're given the general term of our sequence, which is 2n minus 3 all over 3n plus 4, and we're asked to determine if it is increasing or decreasing. In Calculus 1, we learned how to figure out if a function was increasing or decreasing. So we want to relate our sequence, which is not continuous, to a continuous function, because that's what we know how to do. So we're going to relate our sequence with our n values. That tells us we're only plugging in like 1, 2, 3 to a corresponding function with the input x. That tells us that we are using a continuous domain. There we go. So x's. Okay, so once we have decided we're going to use this function, a visual that goes with it, you see on the screen there's some dots. That's our sequence, but this function fits exactly on it. So however the function behaves, our sequence is going to behave right there with it. All right, so last semester we learned something called the first derivative test, and that told us that if the first derivative is positive, then the original function is increasing. And then alternatively, if the first derivative is negative, that tells us that the original function is decreasing. Cool, so let's use that first derivative test to determine if this corresponding function is increasing or decreasing. To take the derivative, we're going to have to use the quotient rule because we have a quotient, 2x minus 3 on top, 3x minus 4 on bottom. If you recall the quotient rule, it's been a minute, so it is g times f prime minus f times g prime all over g squared, where f is the top, g is the bottom of our original function. So g is the 3x plus 4, and the derivative of the top is just 2, minus the top, so 2x minus 3, times the derivative of the bottom, which is just 3. All over the whole entire bottom squared. To simplify, we're going to distribute the 2 to the 3x and to the 4. So we'll get 6x plus 8, and then we'll distribute the 3 to the 2x and the negative 3. So we'll get 6x minus 9 all over the same bottom. We don't want to forget to distribute this negative. It goes to both terms. So we'll get 6x plus 8 minus 6, and then minus a negative, so plus 9, all over the same denominator. Now we can combine like terms. We have 6x and negative 6x. Then we also have the constants 8 and 9. If we combine like terms, the x terms cancel each other out, and 8 plus 9 is 17. Cool. So now we can determine, is this positive or is it negative? So the top is a positive constant. No matter what we plug in, it's not changing that. It's always going to be 17 on top. So that's always something positive we don't have to worry about. Now the bottom is positive because it's squared. So whatever we have on that inside, it's always squared. However, even if it wasn't squared, for our sequence, we're only plugging in numbers like 1, 2, 3, 4, 5. So those are only positive numbers. So even if this wasn't squared, 3x plus 4 is always going to be positive when we're plugging in numbers like 0, 1, 2, 3, 4. So cool, we've figured out that our derivative is always positive. It doesn't switch from sometimes being negative, sometimes being positive. It's always positive. So we can say that our original function is always increasing, which then translates to us being able to say that our corresponding sequence is also going to be increasing all the time. All right, let's scroll back up, make sure we answered that part. So we've decided that yes, it is increasing, no, it's not decreasing. And what we mean by increasing is it's always increasing. So that tells us it is monotonic, mono meaning one, it's only going one direction. So yes, it's monotonic, it is increasing monotonically. It's not going up and down and all around. Next, we want to figure out if it's bounded. So let's go back down to show our work. Okay, so again with the visual, since a sub n is increasing, we're going to start with our a sub 1 and then just keep on going up and up and up and up and up because it's an increasing sequence. So just by looking at that visual, we can tell that the first point is going to be the lowest point of them all. So the sequence is going to be bounded below by our first term, a sub 1. Then to find out what it's bounded above by, we can take the limit as n goes to infinity. Now, if this limit goes to infinity, then it's not bounded by anything. It's just going to go up and up and up and up and up forever and ever and ever. But if we get an actual value, then that tells us it's the highest it's going to reach. We're just going to keep getting closer and closer and closer to that value. And this is again because it's increasing. If it were decreasing, you'd have to use some logic to figure out like a similar scenario. So let's figure out a sub 1. That's what the lowest term is going to be. We're going to replace our general term. Everywhere we see an n, we put a 1. And we get 2 minus 3 all over 3 plus 4, which is negative 1/7. So a sub n, our sequence, is bounded below by negative 1/7. So now let's take the limit to figure out if it is bounded above, and if it is, what is it bounded above by? You'll notice that the degree of the top and bottom polynomial are the same. It's n to the first power, n to the first power. So the shortcut is just to say that the limit is the leading coefficients, so 2/3. In the past, we weren't allowed to do the shortcut because I wanted to make sure we knew it. That's when you could either use L'Hopital's rule or divide the top and bottom by the highest power of the bottom. So just to show that work, if we're not quite comfortable with the shortcut, let's divide the top and bottom by n. That's the highest power of the bottom. So we'll get 2 minus 3 over n all over 3 plus 4 over n. As we take the limit, we get 2 minus 0 plus 3, or over 3 plus 0, which is 2/3. So that shortcut did actually work. Now we can see why. So our limit went to a number. It did not go to infinity. So that tells us, hey, it is actually bounded above by the number 2/3. Now, by definition, since our sequence is bounded above and bounded below, we can say that our sequence is a bounded sequence. So if it's just bounded above but not below, or vice versa, if it just is bounded on one end, it's not. But since this is bounded on both ends, we can say it's a bounded sequence.